Okay, so how can I? Do you see my screen? Okay, can you see my screen? Hmm? So I assume that you guys see this one, yeah?
Yes, sir.
Okay, so I'll just start with this example. I mean, we did all of this yesterday. You remember this was the sample space. Um, yeah, these were the sample points, and these were the values the random variable was assigning. Um, but if you remember, we didn't discuss the individual values. So I just listed them from another example, and when I look there, even there, I mean, they just assigned values without explaining anything. So you need to have an idea of how to assign these values. So if you read this paragraph carefully, the only thing this paragraph tells you is how to write these sample points. So S is for Smith, J is for Jones, and B is for Brown. There are these actually three um, employees, and safety helmets are given randomly to them, and that's all. There is nothing else mentioned in this paragraph. I told you that you have to look for hints in the paragraph of the description of an experiment if you want to assign probabilities. So this says nothing about how probabilities are assigned. So the best bet you can have right now is to look at this sample space. If I now ask you how many sample points are in this sample space, so if S is the sample space, what will be my size of the sample space for this question or for this experiment? Hmm? Yeah, these are the only sample points. 1, 2, 3, 4, 5, 6, right? And there is no information in the question which tells us why the probability of any one of them should be more than any other. Yeah, because for that you need some information. So when there is nothing in there, so all you can do is to assume something, and we can assume equally likely outcomes. So it means that we can assign equal probability to each one of them. So what will be the probability attached to, for example, this one? It will be 1/6, right? And what will be attached to this one? Also 1/6. So now, what is f of 0? F of 0 is the probability of the event, I will say event, in which all the sample points were given 0 as the value. So both these points were given 0. So it means that I have to add these probabilities, right? So that's why it is um, 1/6 plus 1/6, and that is 1/3. This is the reason we get this value, right? So if you follow this reasoning, what will be the probability? So first we look for the sample space. What is the probability of this one? Again, 1/6. Everyone is 1/6 if you look for the events. But if you look for the PMF, this m is equal to 3 is assigned to only one sample point. So the probability here, f of 3 will simply be 1/6 because there is only one point. On the other hand, m is equal to 1 you have 3 points, yeah? So 1 plus 1 over 6, 1 over 6, 1 over 6, yeah? You add all of that. So f of 1 is 1 over 6, 1 over 6, 1 over 6, and that is 3 over 6, and that is 1 half. So, in this is one of those questions where when you are writing your PMF, um, you need to have some model, right? It will not always be equally likely, but at least you should know. So now let's get back to the next topic. We yesterday learned how to plot this PMF, right? This is what we did, and we also learned how to plot the CDF. This is how it looks, right? The only difference is that I made this circle which is not filled and this circle which is filled. I made this explicit. I would expect you to do that. Otherwise, I don't know whether you understand it or not. So if you plot it like this, then I have no way of telling whether you understand this concept or not. There is another plot which he mentions, and that is the probability histogram. So this is very similar to a bar chart. So you can easily get this chart from the PMF by replacing these single bars, single vertical lines with with these rectangles. So you just have that value at the center, choose some width, because this width has no meaning. I mean, you can just keep this width to be 1, and you keep this width to be 1, to be 1, 1, 1. The advantage of this value 1 is that this height is the same and the width is 1, so this area is now giving you the probability. Here, this area is giving you the probability, and so on. So later on, we will find these areas important. So whenever you replace or convert a probability mass function plot to a probability histogram, the idea is to view probabilities as areas rather than simply vertical values, right? So keep this in mind because we are going to start that topic soon. Okay. Yeah, so the next topic, the next section 3.3 is actually continuous probability distribution. So far we were dealing with discrete. So when you say discrete, this is an adjective. So you can, what you mean by this is discrete random variables and also discrete distributions, because the probability distribution you get is discrete. So why do we need continuous distributions? Of course, there are some variables which we know they cannot be discrete, and you know it from signals and systems as well. So for example, if I have voltage, if I measure voltage, and if there is uncertainty about the values, yeah, I'm not sure about whether the value of that voltage is exact or not. So I will model this as a continuous random variable, right? This will be a random variable, but it will be a continuous random variable. Similarly, resistance, yeah, height, these are different examples, mass. So many of the physical quantities you are dealing with, when there is uncertainty, you model them as continuous random variables. That is very easy. That is the easy part. Time, age, yeah, age of someone. And the question is, how do we build their distribution? So if you, I will choose actually some blank page to illustrate this concept. So let's say I have a continuous random variable, and let's say this is in some interval. So I have some interval a and some interval b. It can be any values, and a random variable x can have any value between this interval. So how many points do I have here? Infinite points, right? So, and let's keep this even simpler. So instead of A and B, let's use, let's call this 0 and let's call this n minus 1. So n can be some number. How many values do you have here?
Infinite.
Infinite, yeah. Actually, the way I asked this question, it didn't make it explicit, okay? So I will still go with, let's say, A and B. And I want you to recall what you did in Riemann sums, yeah? So instead of changing A and B, I will just choose these intervals, right? I just choose these intervals and I will choose n intervals. So I will choose these intervals in such a way that the number of intervals is n. So the length of one interval will be 1 over n, right? 1 over n, 1 over n, 1 over n, and so on. And then so you're right that there are infinite points. So if I, and let's say for simplicity that these are all equally likely. Of course, you don't require them to be equally likely, but assume this to understand this point, because I want to make this discussion easy to follow. We don't want to complicate it. So equally likely is the easiest situation, right? Easiest situation to imagine. So if you assign equal probability and you increase this number, yeah, because you want the exact infinity, so n will approach infinity and you will be adding these probabilities. So there are two situations: either you have some tiny probabilities, very small probability, let's use some number epsilon for that, to each one of them. So the total probability will be epsilon plus epsilon plus epsilon plus epsilon, and you'll be adding them. How many times you have to add this epsilon in the limit approaching infinity? You will have to add it infinite times, yeah, and each one of them is non-zero. So what should be the limit? Hmm?
It should add to 1.
N to infinity, because I have infinite number of points.
Yeah.
Of course, if you have if you have 1 over n, 1 over n plus 1 over n, then you can hope that it will become 1, right? But this will only happen if you can distinguish between these points. So if they are discrete points, we are now talking about a continuous. So let me put it this way. Um, you remember you were calculating this Riemann integral in this way, right? You did something like that. This was a curve. You wanted this area, and you did these rectangles, and you calculated. But what if I turn this into a discrete problem? What will I have then? Instead of these rectangles, I want to have these bars, right? So I'm now using a different plot, and I will have bars, right? Bars. No rectangles, only bars. What is the area of each bar? Hmm?
It's a probability.
No, I'm just asking about the area of this bar. Let's say I'm calculating this area, and instead of these rectangles, yeah, this has zero width, right?
Yeah.
So a rectangle with zero width will have zero area. So you will be adding zero, right? So no matter how many times you add zero, the area will be zero. Area will be zero. That's the whole issue. So that's why in Riemann integration, you never work like this. You, instead of working with these points, you work with intervals, right? So it only makes sense to assign area to an interval. If you assign area to a point, all the areas will be zero, and then you will be just adding zeros, right? So here is the trick. And whenever you are, of course, this topic is very advanced. I don't want to discuss this further. But what you need to remember is that whenever you are dealing with continuous random variables, it does not make sense to speak of these individual points because you will always have this paradox. If you use non-zeros and you add non-zeros, yeah, I will say some numbers, infinite number of times, you there is no guarantee that you will get a one, right? It can even go out of bound. But if you are adding zeros, you will get zero, and probability requires a non-zero value for the total. So the best method is to deal with intervals, and that is the reason why I mentioned that you need to keep this in mind. The reason we converted this PMF plot into this histogram because we want to think in terms of intervals, and then we can shrink these intervals. We can make these intervals smaller and smaller, but no matter how small we are in the limit, we will never make these intervals zero width. Yeah, the width will always be non-zero. So it means that you are just adding rectangles. Yeah. Now, now the complication. Let's discuss the complication here. In these two plots, there was no issue. Why? Because the width of each interval was, what is the width of each interval?
1.
1. So the advantage of that is that the area is the same as the height, right? But what if I make these intervals smaller and smaller? What will happen?
The height will go to infinity.
No, no, the height will go to infinity.
Depends on how small the area is.
Yeah, so what if I make these rectangles, yeah? Yeah. And I'm not changing the height. So the area will get smaller and smaller and smaller, right?
So width will be 0, and
Yeah,
then area is 0.
width will uh, approach zero, but what I want you to see is that the interpretation has changed. The height was equal to the area only when this was 1. When this is not 1, height cannot be interpreted as a probability anymore. You see the point?
Yeah.
So height must be given a different meaning. So this small f, we can no longer call it probability. So far we were calling it probability because although PMF is a name, but ultimately it's a probability. How do we define PMF? Probability that x equals x. So it is still a probability. But this requires, in this diagram, we don't have a problem. But in this diagram, this meaning is retained only when we use this width of 1. The moment we start using a different width, we lose this meaning. So that must now have a different meaning. So now I'm asking that question on a different page, right? Now I'm asking a question here. So let me draw a line and I'll ask one question here and one question here. So let's say I have a rectangle and this has a width which is not 1. So let's say this width is delta x. And I am still calling it f of x, but I don't know whether it's a probability or not. And here I am using again delta x, but this time I'm not dealing with probability. Let's say I have some other function. Um, let's say, yeah, let's call it mu, something mu of x. Yeah. And now I'll also give you another plot. So if this width was 1, then I could call this probability, right? And in this example, if this width was 1, I could call this mass. So now I'm giving you two examples. And forget about units. Yeah, let's say we have removed all the units so that we can talk about 1. And so when the width is 1 here, the vertical, yeah, this side can be given the meaning of mass. Here, when the width is 1, we can give it the meaning of mass. When the width changes from something different to 1, can you suggest names for this and for this? This cannot be probability and this cannot be mass. So what name would be correct here? To answer that question,
Maybe relative, something relative to something else.
no, to answer that question, here, what is the area here? The area is also probability, yeah, because probability times 1 is also probability. Here, the area is also mass, yeah, mass times 1. So now, this is not 1, but the area, we want the area still to be mass, right? So if this is length, this must be mass density, right? Linear density. You even studied it in physics. You remember that vibrating string thing?
Yes, sir.
Linear density. So this will be probability density. This cannot be probability because you want the area to be equal to probability. So if the area is probability and the length is not 1, the height, the vertical coordinate must be probability density, which means probability per unit interval, right? Just like here, mass per unit interval. So it will be a derivative of mass. You can say dm by dx, right? And here it will be d by dx of some probability. You got this now?
Yes, sir.
This is the main thing. So everything now changes. The meaning of small f changes, it becomes a density, right? And instead of summing, instead of adding all these, yeah, just like adding these things, yeah. What should we do now instead of addition? We should be integrate.
Multiply and add.
No, integral. Summations will be
Yeah,
replaced with integral.
integration.
Because when you have a density, you don't add densities, yeah. You integrate densities to get. So you integrate density to get mass. You integrate probability density to get probability. So everything changes. Yeah. So this is now, and I'll now write the formula which we learned yesterday. Yesterday we learned this formula that when x was between a and b, right? And remember we had this b here. How we wrote it? We wrote it as summation, yeah, f of x, and x was between a and b. That formula will now be replaced with this formula. Instead of, because this was probability, we could add probabilities. This f now will not be probability, it will be probability density. So we will have to integrate it by multiplying with dx and integrate from a to b, right? And you can even see this, yeah, density, your values of the variable, and the area between any 2 points will give you the probability that x takes values in that interval. Now the question we need to ask here, two questions, and you can actually recover the meaning of small f from here. How should I choose a and b so that I don't see this integral? So you can say, let's choose x, let's choose this as x, and let's choose this x plus delta x, right? And let's say delta x is very small, so this will be nearly equal to f of x delta x, right? And you divide both sides by delta x, cancel it, and now you can easily say that f of x is simply the nearly equal to the probability in that region delta x divided by delta x. So probability per unit interval. That's what we mean by probability density. The other thing you need to keep in mind is that here we were very particular about whether this is equal, less than or equal, or less than, or with this was important. Here it wouldn't matter. You will just see it doesn't matter whether I have this equal sign here or not. Can you guess why we should not care about this here?
Because integration doesn't care about whether it's included or not in the limit.
So why that?
Because we add all the intervals anyways, right? When we integrate.
No, but that is not the main reason. Why does it matter in summation and why does it not matter in integration? Because that will be a single point, right?
Because that
This
was
uh,
discrete. Yeah.
yeah, but here in this it will be a single point. So let's say if I include B, that all I'm doing is to have this vertical bar, right? And what is the width of this vertical bar?
0.
So what is the area of this vertical bar?
Also 0.
So that's why it doesn't matter because these are now areas. So the meaning makes this discussion irrelevant because these are areas and including a single point or excluding it doesn't change the area. But this was not the case with summation. Yeah, in summation each term mattered, right? So what this means is that all these, I'm just highlighting this, all these probabilities are equal. Yeah, it doesn't matter where you have this equal sign or not, but this requires x to be, you must remember this, don't make your own rules. Yeah, this is only when x is a continuous random variable. Don't apply this rule for discrete random variables. Yeah? So when you're reading this equation, do read what is written before it, continuous random variables, right? And the name is probability density function. Some people complain why we are using the same symbol f, right, for discrete random variable and for continuous random variable. So the easiest way to actually um, settle this issue is to look at the type, right? When you write x here, this value will tell you whether it's a value of a discrete random variable or a continuous. So whenever it is discrete, you can, yeah, the meaning of it will change. We do this all the time in maths. You don't need to stick to those symbols. The type of the input will clarify the meaning. These are some typical plots of density functions. Yeah. Now, if you are given such a plot and parts that are not shown are actually assumed to be zero, right? Like this. You cannot leave it undefined, right? Why you can't leave it undefined? Any idea? So my question is, let's say there is a PDF. This question was also about PMF, right? Let's say I have a PMF here, 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 and I'm not using other points. So it must be zero in all at all those points. Because if it is not zero, then I can't calculate probabilities. The reason we use PMFs is that we must be able to calculate any probability of any interval on this real line. So I don't want to have undefined points. Yeah. The same is the case with PDF. If I have a plot of PDF, let's say this is a plot, and if I don't know what is the value of this PDF, then I will not be able to calculate probabilities. Yeah. So it must be zero. And of course, one of the main reason is that these points were not assigned by random variables. So support, yeah, support is the range of values on the real line for which the PDF is non-zero or the PMF is non-zero. So now the question is, how do you check whether a particular plot is just any function or is it a PDF? How will you check it? How did you check PMF? What was the criteria for checking the PMF? You learned it yesterday. Can you give me two criteria? Two criteria for checking PMF. So I have f of x, which is a PMF, and I want to know whether this is a legitimate PMF or not. So what is the first condition? You learned it yesterday.
That the sum should add to 1.
non-zero value.
It must be non-zero. That's the first thing. So if it is negative, then you are gone. So number 2, summation
Should add to 1.
or all the possible values. When I say x, I mean all the possible values. Must be, sorry, 1. Yeah. Now you need to derive a similar rule for PDF. What if f is a PDF? So will the first condition change, or it will be the same? Think about it.
It can be 0, I guess.
Yeah, but it's PDF.
But can't density at a particular point be 0?
Yeah, it can be 0. Yeah, like that. Yeah, but can it be negative? That's what I was asking. Can
No,
PDF be negative? How we looked at PDF? Yeah, it was only a density,
it
right?
can't be negative.
Yeah, it can't be negative. So that rule still applies here. How will the second rule change?
That it should approximate 1, not exactly be 1.
No, it will still be 1, but this operation will change. Instead of summing all possible values, you will be,
Integrating.
yeah, but over the entire real line, right? You have to integrate it over the entire real line, and this must equal 1. So that is the limit, because integral is a limit, so it is exactly equal to 1, right? You use approximations if you are not using this notation. So integral is by definition a limit, so you don't need any problem. You don't have any
Right.
problem with that. So these are the checks which you must actually perform before accepting a given function. So these are now the checks, yeah. This must be non-zero for all real lines, yeah, for all real values. This must be the case. And now we have a new rule that between any 2 points, the integral from a to b is just the probability, and it doesn't matter how, whether you have these equal signs or not. So let's have a simple example, and then we go to exercises for more complicated examples. So the easiest one to start with is this. Suppose there is some reaction, chemical reaction, and you are measuring temperature in that reaction. There is some controlled lab experiment, and you somehow are unable to calculate or to measure the exact temperature. So whenever you measure the temperature, there is an error in it, right? In these chemistry labs or physics labs, you must be aware of these errors. So the error turns out to be a continuous random variable. So he's using this x for the error in this case. And the error in what? Reduction temperature in. So you see why he is doing that? Because he doesn't want to have these units in the formulas. So you just have this in the paragraph so that your symbols are clean without any units. So that is not only a continuous random variable, he's also proposing a probability density function, right? So let's say I give this probability density function to you. How will you check if it's correct? Although this question is not asking you, but you must be. And let's say I ask you to check it for me. What will you do? The first step.
We check non-negativity.
Yeah, so does it pass that check? You have to check it, remember, for every value of x, yeah? So x can either be in this range, and here it is x squared by 3. 3 is positive, and the square of any real number is positive, right? In this range. Non-negative, sorry. X can be 0 as well. So if x is real, right, x squared must be non-negative. When can x squared be negative? Tell me. If I want to say that x squared can be negative, what must be the case? X must be complex, right?
An imaginary number.
Yeah, a complex or imaginary. Because we know X is real here. Yeah, I mean, in this course, because this is the first course, so all the random variables in this course are assumed to be real. Complex random variables are advanced topics. So there you will have to come up with another criteria. But for real random variables, we know that this condition is met here. And for all the other possible values, it is 0, but 0 is also possible, yeah? So it meets that requirement. Now, what is the next requirement? Integrate. So we need to integrate this from minus infinity to plus infinity, f of x dx. So there are two subintervals. One is this and one is this. So this one is from minus 1 to 2, right? X squared divided by 3 dx plus for all the other, it must be 0. Why? Because this is 0 and the integral of 0 is 0. So now can you check this quickly? You can use calculus and it must be 1. If it is not 1, there is some mistake in writing this, right? Yeah, so he's asking you to verify, and then you are asking for the probability. Yeah, he has done this for you, and this turns out to be 1. So how do we compute this probability? Can you use these steps to work this thing out quickly without redoing this calculation? So it will be from 0 to 1, right? Because this is the lower limit, this is the upper limit. And from 0 to 1, you have
The same function. X,
yeah, what should I write in the integrand?
x squared over 3.
Yeah, I can write that because 0 to 1 is a subinterval of this, right? If one of the limits was outside, then I had to break it down into two subintervals. So I can simply use this interval. So it's x cubed over 9 and it's 0 to 1, and you can actually work it out. Turns out to be 1 over 9, right? So let's go to exercise questions. Oh, okay. Now before going there, you can even update your definition of CDF. Remember, this part didn't change. Why? This was the same in discrete as well. How would you explain that? Don't look at the integral yet, yeah? So who can answer this question? Why this part didn't change for continuous random variable? Hmm?
Does the upper limit have to be an arbitrary value and not infinity?
No, the reason is that this is simply a shorthand, right? And this will translate to some event in the sample space. And the sample space doesn't care. Remember, this random variable, you define the random variable on a sample space. You have a sample space, you define a random variable, and you assign values. Whether you assign discrete values or whether you assign continuous values, this is your problem. Sample space is sample space. So this will be just in some event there, and you have an event there, and we don't want this event to change. This will tell us that we are looking for CDF. So this definition must not change, otherwise we will have problems, yeah. So when we were defining CDF, we didn't care whether the random variable were discrete or not. Then let's go back to that part, yeah, because I want to see here. This is the reason, or this summation is because of the discreteness, yeah? If I remove discreteness here, only this part will disappear. This has to be the same because I still want to call it CDF. So CDF of. So CDF of discrete variable, CDF of continuous. This CDF, this was not the case with PMF. So we were using different names, yeah? PMF for random variable and PDF for continuous random variable and PMF for discrete random variable. So there, because the name changes, the meaning changes. We don't want to change the meaning of CDF because we want to use the same symbol and we also want to use the same name. So only the calculation will be different, right? So when you calculate it as a sum, it will be the CDF of a discrete random variable. When you calculate it, so the reason I'm highlighting this thing is that you must not confuse computation with definition, right? So this is how you, sorry. So this part tells you how to compute, and this tells you what are we talking about, yeah? So this is still a CDF, and CDF doesn't care how you compute it. So that's why this definition, this is not a computation, this is a question. And you can easily now see that because differentiation and integration are, no, I get to that later. The lower limit will be minus infinity because there is no lower limit here. Minus infinity means that it's unbounded on the left side, and the upper limit will be x. And if you now differentiate under the integral sign, you can recover your PADF from CDF as a derivative, right? So you always can go back from CDF. You can go to PDF by just differentiating the CDF, and between any 2 points, you can now, this formula is very similar to what you saw in discrete random variable. The only reason it is different now is because of these equal signs, yeah? The equal signs matter in discrete random variable. Otherwise, this looks very same. But this is new formula. So if I now ask you to give me a single formula for both types of variables for the PDF. No, not for the PDF, but for this f of x. So this f of x, we want, this will be PMF in one case and PDF in another case. Because many people use the same symbol, you will also see another terminology in some textbooks, especially in software. If you look for some packages in Python, which are used for computing probabilities, or MATLAB, if you see documentation, they don't use the word PMF. They use the word PDF, but you just write discrete PDF and continuous PDF. You will see this in software documentations. So when you see discrete PDF, what you actually mean is PMF, right? So the reason they use this terminology is to have a single formula, a single symbol for both. So I can now ask you to fill this for discrete random variable x and for continuous random variable x. So if x is the discrete random variable, I want you to write this, and this must come from CDF. So let's say you know CDF capital F. So how will you use capital F for a discrete random variable to get your PMF or discrete PDF? We learned it yesterday. What was it? F of something plus F minus F of something. Can somebody recall that?
And B minus A.
No, this is x. So f of x minus f of x minus, right? The
Yeah.
CDF at x minus the CDF at a previous point, immediately previous. Do you remember this now? This is what we did yesterday. Now, what
Yes,
if you What if you try the same thing for continuous? Let's say you know nothing about continuous and you try this. I showed you already there that the CDF of a discrete random variable, the plot looked like that, yeah, right? So the continuous will be here, right? So what happens in the continuous? There is no difference between f of x and f of x minus, yeah, because it's a flat line, horizontal. So what will be this difference for a continuous random variable if you are using the same formula? It will be zero, right? Because there is no difference between x and x minus and x plus. That is why this symbol small f cannot have a meaning of probability, because if you insist that it is a probability just like it was in discrete random variable, then you get prepared for seeing all these zeros. We don't want to see those zeros, yeah? So what do? We change the meaning, we replace it with density. And density is not this difference, but I'll just reiterate, it is this difference divided by,
Sure.
yeah, that's delta. So that is actually the derivative. So it is now the derivative at x, right? And now I'll tell you, if you have understood these two formulas, right? I can have a single formula, two versions. Now I can also give you a reason why these software developers still use the word PDF, but they just add discrete to it. And the help, you can get the help from that probability histogram. Let's look at that plot again. You can draw this plot even for discrete random variable, right? So what you do, you actually,
Keep area as 1.
because you make it 1 forcefully, you can still call it density by making it 1. So what they do, they think of the formula here. So this is now x minus x minus 1. What is x minus in discrete cases?
1.
It will be 1, yeah? It will be 1. So there is even a name for this quotient in computer science. The mathematicians don't like that name, but the computer science guys call it discrete derivative. So it's called discrete differentiation, right? So it's the continuous derivative and it's the discrete derivative. And the cool thing about this is that you can not only use the same symbol, but you can use the same name and you just call it discrete. And this is what most software tools do. They don't like the word PMF. PMF is only used by those guys who don't use software, right? And because I expect you to use software, so you should be ready to use this name as well, right? So now we need to get to some exercise questions. This was all from the chapter. I will ask you to go through these exercises yourself, yeah? There's nothing special there. So we'll just pick some questions from the exercises. Can you tell me, just go through this first question. Classify the following random variables as discrete or continuous. So what is the first one? The number of automobile accidents per year in Virginia.
Discrete.
Discrete, okay? The next one, length of time to play 18 holes of golf.
Also discrete.
No, length of time. Length of time.
They're continuous here
Yeah, it has to be
because
continuous. Yeah, it will be. I mean, he has made one mistake because in mathematics we have no room for units. Yeah. So how would you change this description to make it mathematically correct? Length of time in, you have to write the units. Yeah. and some units, like in seconds. Because if you don't do that, then time will carry the units, and then y will also carry units, and we don't want to do that, right? This is not physics. So what about the next one? Amount of milk produced yearly by a particular
So
cow.
Discrete.
Amount of milk. Amount of milk. What do you mean by amount of milk? How do you measure milk? You measure in liters, yeah? A liter is volume.
Yeah.
So it's continuous, right?
Mm.
There is only one confusion. If you were doing chemistry seriously, I can expect that confusion, but now you're not doing chemistry. You know, this word amount is used in two ways in chemistry. One is just the amount, and
Moles.
one is the chemical amount, right? And chemical amount is actually the number of, actually it's moles, yeah? So that is amount of substance. We are not doing anything like that here, yeah? This is not chemistry. So this is just the amount, and by the amount you mean, amount can mean volume, it can mean mass, it can mean length, anything. So, but it's still continuous. The next one, number of eggs laid each month by a hen.
discrete.
Discrete, yeah, because you can distinguish one egg from the other. This is the main thing. Yeah? If you can distinguish things from each other, here automobile accidents, yeah, you can distinguish one accident from another accident. And number of building permits, last one, issued each month
Discrete.
in a certain city. The weight of grain produced per acre.
Continuous.
Continuous. Okay, here I want to tell one thing which can confuse some of you, but that confusion is not actually warranted. You should avoid that confusion. When we say there is no confusion with discrete, so I'll only focus on continuous, right? So if I look at, let's say, weight, right, and look for the possible values. So when you are writing values, you will be using floating point, right? Arithmetic. Floating point, you must have used IEEE floating point standard in C++ or any other program. There you must use a finite number of, yeah, digits, because otherwise computation is not possible. So when you are using computer representation of numbers, then everything is discrete. That's why we call them digital computers, right? But that should not be the reason to call this a discrete random variable. That will be a stupid reason, right? Because that is a limitation of technology. And this course is not about technology. This course is about concepts. Conceptually, it is still a continuous random variable. The fact that we have no technology to represent real numbers exactly, that is our problem. That is not the problem of math. So do you understand that?
Yes,
Yeah.
sir.
So technological limitation will never be the reason to change the definition of quantities, right? So continuous will always be continuous. I mean, regardless of whether you can represent those numbers exactly or not. Maybe there are some creatures, yeah, who can do that. So math is not just for humans. Math is for everybody. Let's get to yeah. So instead of solving all the questions, I will only solve two types of questions. Um, let's solve.
Sir,
Yes.
for the length of time, we can still quantize the continuous variable and construct that PMF plot, right?
Yeah, but then you will be changing the meaning, right? You will be actually defining the new random variable, and you will be doing lots of adjustments. Yeah, you can't just quantize. The quantization is done in a
Mhm.
specific way. That is something you will learn in DSP. Okay.
Okay.
So I just want. I mean, we won't be solving everything, but I just want you to try these things. For example, if you look at 3.5, right? So he's asking you to determine the value of C so that each of the following functions can serve as a probability distribution of discrete random variable, right? Discrete random variable. So which means PMF. So how will you check that this is a legitimate PMF? You are not asked for checking, you are asked to compute C to make this a PMF. So what will you do? The first condition is that this must be non-negative, right? So x squared plus 4 is already non-negative, yeah? But actually this is positive because plus 4 x squared cannot be negative. So x squared plus 4 must be non-negative and C must be non-negative. So the first condition is that C must be non-negative. And then these are the possible values. So I will just say f of 0 plus f of 1 plus f of 2. I'll plug these values there and this must equal 1 and that will give me the final value of C, right? So if this was a question about PDF, right? Yeah, here is now the next question is about density. So you are given a no, but this doesn't ask for a particular value. There must be some question where he's asking for a value. So yeah, this one. Yeah. Let's say you are given a proposed density function, but k is not fixed. Yeah, you are asked to find k to turn this into a PDF. So what is the first thing you need to check? This must be non-negative, right? So that requires k to be
Greater than 0.
no non-negative.
Yeah.
Yeah, and this thing, why are we sure that this will always be non-negative?
Because x is a real number.
Yeah, and what is the meaning of this symbol? That's not the only reason. X, what if x is negative, right? You have a problem, right?
Sir, imaginary 11.
Yeah, but you have to read the question. What is the interval for which
It's
this?
from 0 to 4.
Yeah, so you have to read this. So you need to have a justification for why this is non-negative. So two reasons. One, this never gets negative. The second reason is that this symbol is only used for the principal square root. Okay? You cannot say this will be plus minus something. That plus minus is wrong, right? So we know this is a principal square root, so we'll only go look for the positive square root or 0 when it is 0. And it is 0 elsewhere. So the next thing you need to do is to integrate from minus infinity to infinity equals to 1 and then solve for k. So this lecture goes till you need to start typing P in the chat window, right? Each one of you, right? Somebody needs to tell me the time until which this lecture has to go, or I have to check it because this tracker for some reason doesn't work. So it's Ramzan. Yeah, we still have some because you're writing P, so I'll just discuss one more question. Let W be the a random variable giving the number of heads minus the number of tails in 3 tosses of a coin. List the elements of the sample space for 3 tosses and to each point assign a value W. So how will you go about it? 3 tosses. So sample points will look like this. Head, right? Head, tail, head, and so on, yeah? So just, I want to know whether you understand this thing. what will be the values of W here? Number of heads minus the number of tails. What do you get here? 3. And here?
1.
Okay, 1. And so on. And in this case, it will be 1. So
Yeah.
if it was T, 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 H, it will be minus
Minus
1, right? Yeah, so on and so forth. And how do you assign probabilities? There are 2 ways. One way is all are equally likely, count it, 1 divided by that. The other thing is that equally likely is because head and tail are equally likely. So half times half times half, which is 1/8, right? So if our W will be 1/8. If it is only, if there are multiple points, you have to add. So it's a similar trick. That was all, okay? If there are any question, you can ask in the next 2 minutes.
Sir, could you explain how you assigned probability again to the heads and tails question?
How did I assign the probabilities? 1/8?
Yeah.
Okay, let me just do this.
You assumed equally likely?
Yeah, equally likely. And when you assume equally likely, it can be done in 2 ways, right? One,
Hmm.
one is to just list all the things, yeah. So how many entries do you have? 2 to the third, yeah, by counting, which
8.
is 8.
Hmm.
So 1/8, yeah. Each one is 1/8.
Right.
But if you don't want to do that, then you think of it as a 3-stage experiments, yeah. So the first part, which would be either a head or tail, second either a head or tail, third either a head or tail, and these are independent. So this is 1/2, this is 1/2, this is 1/2. Product rule, yeah.
Hmm. Okay.
So this you get with the sum rule, and this you get with the product rule. And one of these will be easier in some way, I mean, depending on the question. So you should have both of these methods in mind, right? Okay, we need to actually stop at this point.